Okay, we're going to talk about radioactivity today and nuclei. Now, before we talk about nuclear physics, just want to give you some notation rules so that you understand what people mean when they're talking about nuclei. Now, of course, an atom is made up of a nucleus and electrons that go around it. And so when we talk about the nucleus, we're also, oftentimes interchange talking about the nucleus and the atom, because whatever the nucleus is, whatever the charge of the nucleus is, determines how many electrons go around it when it's a neutral atom. So, when I talk about carbon, I may be talking about a carbon atom, or I may be talking about a carbon nucleus. From the context, it should be clear. Alright, so the atomic number of an atom or a nucleus is the number of protons in the nucleus. And we give it the letter Z. Alright, so Z is the variable which represents the atomic number. It's the number of protons in the nucleus, which is also then going to equal the number of electrons in a neutral atom that has this nucleus, because the number of protons and electrons are balanced in a neutral atom. Alright, so if we don't have an ion, kind of your regular, ordinary, run-of-the-mill atom, it's going to have equal number of protons and neutrons. Z is the number of protons. We call it the atomic number. Now, the atomic number determines which element it is. So if I say carbon, I've got a carbon atom or a carbon nucleus, immediately you know that the atomic number is 6, because Z equals 6 is always carbon. Alright? Now, the reason that the atomic number determines a nucleus is made up of protons and neutrons, right? The number of neutrons does not change which atom it is. Why? Because mostly when we do, chemical reactions and things, what's really going on are interactions between the electrons, and the number of protons determines the number of electrons, and so in a sense the neutrons just come along for the ride when we're talking about chemical things. Alright? But when we get into the nucleus and nuclear decay and fission and fusion and things like that, then the neutrons make a big difference. Alright? So a chemist cares less about the number of neutrons and more about the number of protons, but a nuclear physicist cares about both. Alright? And that is why the atomic number Z determines which atom it is, determines what name we give it, whether it's carbon or silicon or nitrogen or oxygen, right? That has to do with the atomic number Z. Then there's the neutron number N, which is the number of neutrons in the nucleus. Alright? And then there is what we call the mass number, or the atomic mass number A, which is the sum of the two. It tells us how many neutrons and how many protons. Why do we call it the mass number? Well, it turns out that neutrons and protons weigh about the same. They're about the same mass. So if I add the number of them together, I get something which is roughly proportional to the mass of the nucleus. And now the electrons are a lot smaller than protons and neutrons, so the mass number is also roughly proportional to the mass of a neutral atom, or even an ion for that matter. The electrons don't matter as much, right? So that's why we call it the mass number, but it's really just the sum of the neutrons and the protons. Alright, so for any given atom, the atomic number, the neutron number, and the mass number are all integers. Alright? Now, we use a type of notation sometimes to describe atoms or nuclei, where we put the atomic number, the mass number here, the atomic number right here, and then the symbol that represents the atom. For example, if I have a carbon atom that has 6 protons and 6 neutrons, I would call that carbon 12, right? Because its mass number is 12. When I say carbon 12, that 12 is the mass number, and carbon tells me the atomic number. Alright, so carbon 12 would look like this. 6 carbon 12. Alright, so it's carbon, it's got 6 protons, and the sum of protons and neutrons is 12. Alright, now because this 6 always goes with carbon, sometimes we leave the 6 off, and I could write it like this. Just carbon 12, write that. And I know in my mind that there's 6 neutrons, or 6 protons, because carbon, that's what makes it carbon, right? Or I could have calcium 40, alright? Has 40 nucleons in the nucleus, the sum of the protons and the neutrons. I could write a 20 here, alright, to tell me that there's 20 protons, but as soon as I say calcium, you know it's got to be 20. You look up on the atomic table and you say, oh, calcium has 20 protons. It has an atomic number of 20. Alright? Now, an isotope isotopes are two nuclei of the same element. They have the same Z, but they have a different number of neutrons and therefore a different mass number. All right? So for example, carbon-14 is an isotope of carbon-12. All right? So as far as nuclear physics goes, they're very different because the nucleus is different. But as far as the chemistry of carbon goes, they're very similar because they have the same number of protons, which means they'll attract the same number of electrons. All right? So an isotope is something, the same element, same Z, but different N, which means different A. Okay, so there's the notation. All right? So if you see a symbol like this on the homework or the exam, you're immediately going to say, 6 protons, 8 neutrons, right? Or if you see something like this, you'll say, carbon. Well, carbon, I look it up in my periodic table. Carbon is element number 6, so it's got 6 protons, even though I didn't write the 6. That 12 up there means that it's got 12 protons plus neutrons, 12 nucleons. Therefore, it must have 6 protons and 6 neutrons. All right? Okay. Now, what holds the nucleus together? It's something called the nuclear strong force. All right? It's a short-range attractive force between nuclear particles. It turns out it holds the atoms together. It's very short range, so the atoms, the nucleons, the protons and neutrons, have to almost be touching before the strong force really is strong. But then when you get really close, it gets really big. So it's a force that gets really big as you get close. All right? So if the distance between two protons is greater than about 10 to the negative 15 meters, then the Coulomb repulsive force is too strong and the nuclei breaks apart. So the basic idea is like this. All right, so if I were to draw like a potential well that shows, how much energy there is for two protons as a function of distance. All right, here's 0. Way off, far away. All right, these protons have basically 0 interaction. Right, the potential 0. As you get closer, these two protons have a positive charge, and so they're going to repel each other. But if you get close enough, suddenly the strong force kicks in, and if my protons are, so here's the origin of my coordinate system, if my protons are closer than about this, then the strong force overwhelms the Coulomb force and they stick together. But if you get further away, right, the strong force drops off very quickly, and then the Coulomb repulsion kicks in and your protons get pushed away. So in order to get two protons together so that they can stick together in a nucleus, you have to overcome this, what we call the Coulomb barrier, the repulsion at long distances, so they can get close enough for the strong force to kick in and make them stick together. All right. Now that nuclear strong force, in combination with the repulsive Coulomb force, causes the nucleus to bind together, and there's a certain amount of energy then that binds everything together. All right. So if I have these two sitting right here, kind of this energy right here is the binding energy. All right, it's the energy that if this, I would have to somehow put this much energy in to get my proton back here, or if this were a proton and a neutron or whatever, so if I have two neutrons or a proton and a neutron, there's no Coulomb barrier anymore, and you're just going to have something that goes like this. Anyway, the energy to pull my nucleus apart and get all of the particles separated is what we call the binding energy. Now, how can you figure out what the binding energy is of a nucleus? Well, I guess you could take a nucleus and pull nucleons out one at a time. Grab a proton, yank it out. Grab a neutron, yank it out. All right? That's a very difficult experiment to do. So if I want to know the binding energy of a nucleus, there's an easier way to figure that out. And that's because E equals mc squared. All right? So the point is, if I have all of these nucleons, and I put them together, if I'm holding them together, right, energy leaves the system. So if I have say a neutron and a neutron out here, they're fine. All right. Once I stick them together, energy is lost because it takes energy to pull the neutrons apart to get them apart like they were before, right? So when they come together, they lose energy, and that's the binding energy. What that tells me then, if I lose energy, that tells me that the mass of this pair is going to be less than the mass of them separated. All right? So I can figure out the binding energy. The binding energy is just going to be the difference in the masses times c squared. It's going to be the difference in the mass for all the particles separated versus all the particles bound together times c squared. All right? And so if I take, for example, let's say I have carbon 12, and I want to know what is the binding energy of carbon 12. How much energy would it take to separate the carbon atom into all of its pieces? All right, well, what you can do is you can say, well, it's just change in mass times c squared. What's the difference in mass? Well, I've got 6 protons, so the mass of 6 protons plus the mass of 6 neutrons, 6 times the mass of a neutron. All right, and I'm going to compare that to the mass of my nucleus. All right, my carbon 12 nucleus. Multiply that by c squared, and that's the binding energy. Now, of course, you have to be careful because if you look up in a table of atomic masses, probably it's not going to give you the mass of the nucleus. It's going to give you the mass of the atom. And the atom, this atom, along with these 6 protons, there are 6 electrons, right? And those electrons have binding energy as well, right? But it turns out the binding energy of electrons is really small compared to the binding energy that holds the nucleus together. So we can neglect typically the binding energy of electrons and just say, well, look, I've got 6 protons and 6 neutrons. And okay, so when I'm all done, once I've torn my nucleus apart, I've also got these 6 electrons that are sticking around because, you know, if I start with the mass of an atom and then subtract the mass of an atom. All right? And that's how you can find the binding energy. That's how much energy is inside of a nucleus, how much is holding a nucleus together. And it turns out that binding energy is pretty big, which is why nuclear power is such a cool thing. We'll talk more about that later. Now, nuclear decay can only happen if the energy is there to make it happen, right? Now, you can make nuclear reactions where you have some nucleus and you whack something into it and you give it energy, right? And that's another story for another day. But nuclear decay, what happens if I just have this nucleus and it spontaneously decays? That can only happen if it's energetically favorable, all right? So I've got some uranium nucleus and it spontaneously splits, right? Or I have some atom that emits an alpha particle or something, or emits a proton or a neutron or something, all right? Nuclear decay can only happen if it's energetically favorable. What that means is I have this nucleus that I start with, and it has some mass of my nucleus, all right? Afterwards, I've got all my decay products, right? Maybe, you know, I've spit off an alpha particle or an electron or something. The point is, if this has more energy than this, I can't just spontaneously get there. If this has less energy, that's okay because I can give some energy into like kinetic energy. So if this stuff, if its rest energy is less than this rest energy, that's okay because I can give it some kinetic energy to make things happen. So nuclear decay can only happen if this mass, the mass of the nucleus, is greater than or equal to the sum of the masses of all of this other stuff that I'm left with when I'm done, right? Whatever I'm left with when I'm done. So if I came along and said, hey, can carbon 12, can it undergo alpha decay? And you say, well, I don't know. One thing I can check is to see if it's energetically possible. And so I'm going to say, well, is the mass of a carbon 12 nucleus, is that greater than or equal to the sum of the mass of, let's see, if I get rid of a carbon 12 by doing an alpha particle, that would be element 4, which is, oh gosh, I can't remember, element 4. And how many nucleons? I get rid of 4 nucleons. Anyway, so the point is I look at the atom I'd be left with, add that to the mass of my alpha particle that's being spit out. So I take the stuff I'm left with in the end and I compare the mass of that. I don't need the sum sign here because there's just 2 things. Anyway, I take whatever I'm left with in the end and compare that with the mass of what I started with. If this isn't less than or equal to that, then there's no way that decay can happen, all right? Because it's not, it would require extra energy to go into the system to make it happen. Now, so at what time does nuclear decay occur? Imagine I've got some radioactive nucleus and it decays. How can I predict when it occurs? Well, the answer is you can't. This is one of those weird quantum probability things that really the nucleus is constantly moving into a superposition state where it's in a superposition of decayed and hasn't decayed, but then you're constantly measuring it if you're looking to see if it's decayed or not. All right, so it's this quantum probability thing where it'll just happen at some time. All right, so let's imagine it's random. Let's take a simpler problem. Let's imagine I start with n dice, a bunch of dice, and I'm going to roll all of them, and then I'm going to pick them up and roll them again. But every time a die comes up with a number 6, it's thrown out. All right? So this is like nuclear decay, right? In a certain amount of time, some fraction of them will decay, but it's random which ones it will be. All right? So let's imagine this. What's going to happen? Let's say I start with 10 dice. All right? After one roll, 1/6 of them are going to be gone. So after one roll, I'm going to have 5/6 times 10 dice, right? And then after my next roll, I'm going to get rid of 1/6 of these. So I'm going to be left with 5/6 squared times 10 dice, and so forth. And I get something that looks like this, which is an exponential shape. So the decay of my random rolling dice is it's an exponential curve, and I'll show that to you in a minute. All right, more specifically. But right now you should be maybe bothered by the fact that here I start with 10, and here I have a fractional number of dice, and I can't have a fractional number of dice. That's just really weird. And then you realize, oh, this is all about probability, right? When I roll my 10 dice, it could be that all of them come up 6 on that first roll, and they're all gone. Or it could be that none of them come up 6, right? So really, there's lots of different possibilities. So what I did is I had a computer do kind of random numbers, and I took a bunch of different, I took 10 dice, rolled, got rid of all the 6s, and I was left with this. Then I rolled again, got rid of all the 6s, I had this. Rolled again, got rid of all the 6s, and I had this, and so forth. And all of these lines are different trials that I did, right? And the point is that this line here is something like an average-ish, all right? It's somewhere in between the extremes, all right? And the other point I want to make is that as we add more and more dice, all right, the deviation from this average gets smaller and smaller. So with 10, right, I've got all these lines here. Now I could have had, I roll all these times and none of them went away. I could have rolled the first time and gotten rid of all of them, right? But those are very unlikely, right? It's kind of like that entropy argument. There's a lot more paths close to the average than there are far from the average. And as I increase the number of dice, it becomes a lot more improbable to be significantly away from the average. So here's my experiment done with 10 dice. Here's my experiment done with 100 dice. Here's my experiment done with 1,000 dice. And you can see all of my experiments stayed pretty close to the average, because it's very improbable to do something very different from the average when I start with a large number of dice. So in the limit, as I have an infinite number of dice, I pretty much get this average, right? This curve right here, all right, defined by the little dots, all right? So this is a little bit like thermodynamics. I have random things happening, but it's very unlikely to deviate much from kind of what I expect. Okay, and here's 10,000 dice, even better. 1,000, 10, 100, 1,000, 10,000. All right. Now, how much does the number of dice change with each roll? All right. So the idea was, typically on average, the change in the number of dice that I have is the number I start with times the fraction that I lose, right? This is my 1/6, right? And there's a minus sign right here because the number of dice that I have goes down by this amount, if that makes sense. All right? So now, but when we talk about nuclei don't just like, it's not like rolling the dice that every second there's a chance for them to decay. They're continuously having chances to decay. So I'm going to write sort of a more differential version of this. Imagine in a tiny, tiny infinitesimal amount of time, there's some probability that any single nuclei will decay. And so that probability we call the decay constant, lambda. All right, this is not wavelength. We're recycling lambda. Now it means the decay constant. All right, so this is like the fraction of nuclei that will decay in this amount of time. This is like our f. All right, and then I'm going to replace delta n with dn, because if my time is really, really tiny, the number that decays is going to be really, really tiny as well, all right? And so there you have it. This is kind of a more continuous version of this equation right there. And then I'm going to say, well, at what rate do nuclei decay? The rate is the number of decays per unit time, but dn is going to be negative, right? If I have one decay, that means the number of nuclei went down by one, so I need a minus sign in front. So the rate at which radioactive decays occur is negative dn over dt, which is just, right, solving this equation right here, divide by dt, I'm left with n times lambda. And this sort of makes sense, all right? So a bigger decay constant means more decay per unit time, all right? So that's going to be a bigger rate of decay. If I have more nuclei, right, if I have twice as many nuclei and they're all decaying the same way, then I should get twice the rate of nuclear decay. So this is the rate of nuclear decay, and it's that right there. Okay, now the number of decays per second is just lambda n, right? We showed that on the last page. Sometimes decay rates are measured in curies. It turns out that 3.7 times 10 to the 10th decays per second is 1 curie. And this is roughly the rate of 1 gram of radium-226, all right? Because it's named after Marie Curie. She was working with radium a lot, and so this was sort of a natural unit to compare things with, you know, comparing other things to how radium-226 decayed. But the SI unit is the becquerel. It's 1 decay per second. All right, that's what we use in the SI system. Now, of course, decays are kind of like non-real units, kind of like radians. They're units we can get rid of if we need to, and we can make them pop into place when we do need them. So a becquerel is an awful lot like a hertz, an inverse second. All right, but because we're talking about radioactive decays, we call them becquerels. All right. Now, imagine I start with a bunch of nuclei, and I want to know how many there are left after some time t. Well, I know how fast the nuclei decay, but that decay rate depends on how many there are. So as my nuclei decay, the rate will go down. All right? And we had this equation right here, right? The decay rate is negative dn over dt, which is lambda n. So the change in n with respect to time is just negative lambda n. This is the equation that will tell us how n changes with time. All right? This equation is a differential equation. I'm guessing most of you have not taken a class in differential equations, and differential equations can be hard, if not impossible, to solve. This one, however, is easy, so I'm going to show you what we're going to do. We're going to take this, and this is just a little change in the number of nuclei divided by a little increment in time. What I'm going to do is I'm going to manipulate things. First, I'm going to take the dt to the other side. So this is going to be minus lambda n dt. And then I'm going to get everything that depends on n explicitly on this side, and everything that depends explicitly on time on this side. Well, this is a constant. This depends on time, this depends on n, this depends on n. So I'll just divide both sides by n, and I'll be left with dn over n is equal to minus lambda dt. All right? And then I just integrate both sides. I'm going to integrate this side from time 0 to some time t. And as I go from time 0 to time t, I'm going to go from having all the nuclei I started with, n naught, up to how many I have left after a time t, right? So corresponding ranges, limits on my integrals. All right, so now I just do this integral, and the integral of 1 over n is just natural log of n, so this side becomes natural log of n over n naught, right? When I stick my limits in, I have the difference of two logarithms, and I get this. On this side, well, lambda is just a constant, so it comes out, and you get minus lambda, and the integral of dt is just t. Evaluated across these limits, you just get t. All right? Now I'm going to exponentiate both sides. I'm going to raise both sides. I'm going to take e to the power of this and this. All right? E to the power of natural log of n over n naught is just n over n naught. And on the other side, I have e to the power of negative lambda t. Then if I take n naught to the other side, e to the minus lambda t. All right, so here is an equation. If I know how many nuclei I start with, and I know the decay constant for that particular nucleus, I can tell you how many are going to be left after some time t. All right? I can also tell you the rate after some time t, because rate is just n times lambda. So the rate at some time t is just lambda times n, which is lambda n naught, e to the minus lambda t. But lambda n naught is just my initial rate, right? So Anyway, I can do all of this stuff by solving this differential equation. Okay, the half-life. Now, lambda is our decay constant, right? Another way, though, to describe how quickly a bunch of nuclei will decay is the half-life. And the half-life is defined to be, so T, call this T 1/2. The half-life is the time it takes for half of my nuclei to decay. So if I start with 1,000,000 nuclei, one half-life later, I'll have 500,000, right? Now, it's probabilistic, but in the limit of lots and lots of nuclei, right, it becomes pretty absolute, okay? So, how does the half-life relate to the decay constant? Well, remember, n is equal to n naught e to the minus lambda t, all right? So, but if I plug in one half-life for my time, I should have half of my nuclei left. So after one half-life, I have this many left, but that's equal to n naught e to the minus lambda, and I plug in one half-life for my time. So if I plug in one half-life for my time, the number of nuclei I'll have left is half of what I started with. So now I can cancel these out, all right? Now take the natural log of both sides. Natural log of 1/2 is equal to natural log of this, just gets rid of the exponentiation, and I'm left with negative lambda t to the 1/2. But let's take the negative to this side, and negative natural log is the same as natural log of 1 over the thing argument inside. So this is just natural log of 2 is equal to lambda t to the 1/2. So if I know the half-life, I can find the decay constant, right? If I know the decay constant, I can find the half-life, and they're just related by this natural log of 2. And of course, they're inversely related. A bigger decay constant means it decays faster, which means there's a shorter half-life. Okay. Radiocarbon dating. It turns out that you can use radioactivity to date things, to figure out how old something is. One example of this is radiocarbon dating. All right, so it turns out that most of the carbon in the world around us is carbon-12. It's 6 neutrons along with 6 protons. All right, but there's constantly carbon-14 being created in the atmosphere. All right, so carbon-14 is being made in the atmosphere. There's reactions going on in the atmosphere that's generating carbon-14. All right, or reactions around the world, yeah. And so you're constantly breathing in air that has carbon-14 in it. All right, the plants around you are respirating, they're bringing in that carbon-14, and you're eating it, and it's becoming part of you. So there's a certain fraction of the carbon in your body that is carbon-14. It's this radioactive carbon. Now, it doesn't kill you because there's not a lot of it, and it has a fairly long half-life, so not much of it decays while you're alive, all right? It has a half-life of about 5,730 years, all right? But once you die, you stop eating, you stop breathing, you stop bringing in carbon-14, and over time that carbon-14 will decay. So if I were to take an ounce of your flesh and characterize it, look at the nuclei in it, and measure how much what fraction of your carbon is carbon-14, right, I would get some number. 5,730 years after you die, if I take an ounce of your flesh and measure the nuclei in it, I would find that there was half as much carbon-14 around. So the ratio of carbon-12 to carbon-14 would change, right? The fraction of carbon that is carbon-14 would go down by a factor of 2. So you can tell how long something has been dead by measuring the ratio of carbon-12 to carbon-14, all right? And it's an exponential decay. So what you can do is you can say, look, in this ounce of flesh, of this, woolly mammoth, there should have been, initially, for that much of flesh, there should have been some number of carbon-14 atoms. But instead, you measured this much. But you know that n is equal to n naught times e to the minus lambda t, all right? Knowing the half-life, we can find the decay constant. With the decay constant, we can plug this in here and solve for time. And now you know how long ago that woolly mammoth died. All right, now there's some limitations to radiocarbon dating. First of all, has carbon-14 been produced at the same rate throughout the entire history of the world? Well, no, there are fluctuations in that. So the trick here is you can get a good estimate with this, but you can do even better by calibrating. You can look, and you can, if you have other ways of dating things, you know, if you have another way to get a date on something, then you can figure out, oh, knowing the time, right, and I know what fraction of carbon I have, I can then kind of calibrate my carbon-14 dating for things near that time. And then I can go and use radiocarbon dating to date other things. All right? Another problem is the half-life is pretty long, so you're not going to be able to tell how long something's been dead to within, like, days, right? This is for things that have been dead for a long time, and you want to get kind of an answer to within several years of, you know, tens, hundreds of years, how long ago it died. Another problem is for things that are really, really old, maybe there's not much carbon-14 left. But it's a very, very powerful method. There are other things similar to radiocarbon dating. For example, people can tell when rocks formed, because, you know, when a rock is molten, when lava solidifies, well, it's molten, gas can get out of it, right? But once it solidifies, anything that decays and makes a gas like argon, those argon atoms can get trapped inside the rock. So you break open the rock and you say, how much argon is in there? Let's compare that to the radioactive isotopes in the rock that could be making argon, and you can determine how long ago that rock solidified. So really powerful techniques you can use with nuclear decay. Now, it turns out there's several types of radioactive decay. The most commonly discussed are gamma radiation, beta decay, and alpha decay. All right? Now, it turns out alpha decay happens when a nucleus spits out what's known as an alpha particle. And it turns out an alpha particle is just a combination of 2 neutrons, 2 protons. It's basically a helium-4 nucleus. Turns out that that combination is very stable. It has very high binding energy. So a nucleus can maybe reduce its energy by spitting out an alpha particle. All right? And so that the overall binding energy increases. All right? So that's one type of decay. Turns out alpha decay, these particles are charged and they're fairly massive. So alpha particles don't penetrate your skin very much. So usually alpha emitters aren't as dangerous as other types of radioactive materials. You want to be careful not to eat them, because inside your body they can cause a lot of trouble. But typically they aren't too dangerous because they're stopped typically by your skin, or if they're in a container, the alpha particles can be stopped by the container. Alpha decay happens in the Earth, and that's why we still have helium inside on our planet, right? We mentioned in thermodynamics that helium is light enough that helium tends to get up into the upper atmosphere and fly away and disappear from the Earth. But we have a constant supply of helium being made by radioactive stuff decaying inside the Earth. All right? The other type, next type of decay is beta decay, and there's actually 3 different types of beta decay: beta plus, beta minus, and electron capture. The idea with beta decay is a nucleus, a neutron can turn into a proton by emitting an electron. A proton can turn into a neutron by emitting an anti-electron, a positron. Or a proton can become a neutron by capturing an electron. And that's what beta decay is all about. So beta particles are electrons, all right? They're lighter, and so they tend to travel faster and be more penetrating, but they are also charged, so they also interact with things. And so beta particles are more dangerous typically than alpha particles, but they do eventually get stopped by stuff, right? The last type of radioactive decay that we commonly discuss is gamma decay. And gamma decay is the emission of a photon. So what typically happens in gamma decay is some type of nuclear event happens. You know, maybe alpha decay occurs, or I have fission or fusion or something. But in the end, I end up with a nucleus that's in an excited state, all right? And so it can lose energy to go to a lower state by kicking off photons. And these are very energetic photons. They don't have charge. They tend to penetrate things a lot. So gamma radiation is harder to shield and can be very dangerous. All right. It also turns out there's other types of decay. Sometimes a nucleus will spit out a neutron, and sometimes a nucleus will just spontaneously split in half. That's what we call spontaneous fission. Those don't tend to get talked about very much because they tend to happen very quickly. So you don't just like has some radioactive stuff that's been in the Earth for millions of years, and all of a sudden one day it spits out a neutron. That's less typical. More typical is I have some other type of decay. After that decay, the nucleus is in some excited state, and it de-excites. It loses energy by spitting off a neutron or doing spontaneous fission. All right. Later we're going to talk about fission and fusion. Those are not decays. All right. Well, spontaneous fission is decay, but typically when we talk about fission and fusion, we're talking about a reaction where I whack something with a neutron and make this happen. So that's not a decay, that's a reaction. That's responding to some input. And that's all you get on nuclear physics for today.